I will present Apollo, a scalable and coordinated scheduler for cloud-scale computing. Apollo has been deployed at Microsoft to schedule the cloud-scale big data processing workload, and it is joint work between Jaliya, Wei, Bing, and Jingren from Microsoft, and Zhengping, Ming, and Lidong from Microsoft Research. So first, we talk about the workload schedule, essentially cloud-scale big data jobs. Users typically write these jobs in high-level SQL-like language. So for example, at Microsoft, those jobs are typically written using a language called scope. And we have an example here where a user compute the average of latency grouped by market over a large unstructured data set. These jobs are compiled, and the query plan is represented as a DAG. In that DAG, the vertices are tasks, which represent the basic unit of computation. And tasks sharing the same computation, but processing different units of, essentially different partitions of the input are grouped together in stage. The execution of such job is driven by a scheduler. Now, the goal of a scheduler is to minimize the job latency while essentially trying to maximize the overall cluster utilization. Now, at cloud scale, you can imagine that there are tens of thousands of such jobs running in parallel in very large cluster running commodity hardware interconnected with an oversubscribed network. In this context, scheduling actually becomes quite difficult, mainly due to three challenges: the scale involved, the complexity and heterogeneity of the workload, and the difficulty to maximize utilization. First, we talk about the scale. In order to support today's workload, the scaling is very difficult. The jobs that we schedule can process gigabytes to petabytes of data at a time. Collectively, they issue peaks of over hundreds of thousands of scheduling requests per second. The cluster hosting those jobs, so this is some data from our environment, the cluster hosting those jobs contain over 20,000 servers, and we observe them running more than 170,000 tasks in parallel. So the challenge here is how to make optimal scheduling decisions at full production scale. Second, the workload is very complex. Tasks are heterogeneous in many dimensions. They can run from seconds to hours. They can be I/O bound or CPU bound. They can require as little as 100 megabytes of memory to tens of gigabytes of memory. And short tasks, on one hand, are very sensitive to scheduling latency and any overhead introduced, while long I/O bound tasks are actually still sensitive to locality. So the challenge here is how, given this number of different factors, how to make optimal scheduling decisions. Finally, beside being large, the clusters which are hosting these jobs are also very expensive. So we really want to effectively use the resources in order to minimize the amortized cost of each job. However, we need to maintain performance guarantees to our user even under peak load. And this is made difficult with the constant underlying variation in the workload. Below, we show a graph of the number of jobs running in parallel in one of our clusters over the duration of 2 weeks. And we show that beside the small and constant variation in the number of jobs, there's also very large variations. So for example, the number of jobs drops by 40% every weekend. So the challenge here is how to maximize the utilization of cloud scale clusters while maintaining performance guarantees with this dynamic workload. So we've covered the high-level challenges. We now give an overview of how Apollo addressed those challenges. So how it scales using a distributed and coordinated architecture, how it optimized job performance using estimation-based scheduling, how it handles cluster dynamic with conflict resolution, and how it maximized the utilization using opportunistic scheduling. In order to meet the scalability challenge, Apollo adopts a distributed and coordinated architecture. In this architecture, the complex task scheduling logic is distributed among many schedulers, essentially one per job. The schedulers are each making decisions independently. However, since the schedulers are distributed, they only have some partial information about the state of the cluster. So a coordination mechanism is needed. the architecture includes a coordination mechanism which allows the schedulers to make decisions informed by global information. Here we illustrate how it works in practice. There are 2 jobs, each with their own schedulers hosted in the job manager. And there are 3 process nodes, which are essentially servers running tasks on the behalf of jobs. We see the job managers are making scheduling decisions independently, and they're directly dispatching tasks to the process node. We highlighted the need for a coordination mechanism. This is achieved by the process node are periodically sending status updates to a resource monitor. Now, the task of the resource monitor is very simple. It simply aggregates status updates and makes it available to the scheduler to then inform further scheduling decisions. One important design decision that we made is rather than only allow the schedulers to schedule tasks when they are resource available instantaneously, we actually allow a queue. We actually essentially use a queue at the process node, which allows the scheduler to reason about future resource availability and defer conflict resolution. So this architecture allows the scheduler to scale by distributing the complex decision-making across many schedulers and informing those decisions with global information. We highlighted the coordination mechanism, which provides global load information to the schedulers. We now consider how to represent the load of each server in a cluster. The server could represent all the details of the workload running on them during the status update. However, this would be very verbose. Also, given the heterogeneity of the hardware and the workload, it would require the scheduler to understand all the details and constantly reason about this. So instead, Apollo introduced a new abstraction. Rather than exposing the current load on the server, Apollo essentially exposed a schedule of the future resource availability on the server. This abstraction is captured in a wait time matrix, which essentially represent the wait time to acquire resource of a certain size. So here in the example, it would take 10 seconds to acquire 4 CPU cores and 8 gigabytes of RAM. This abstraction has a few nice properties. It's hardware independent, so it masks the underlying heterogeneity of the hardware. It captures the complexity and heterogeneity of the workload with short and long-running tasks and tasks with varying resource requirements, and it's also lightweight and allows for frequent status updates. Finally, it enables the schedulers to reason about future resource availability. And this is important because the availability to reason about future resource availability allow Apollo to proactively trade off between often conflicting factors, for example, I/O locality and wait time. Here's an example of why this is important. In this simplified example, there's an I/O bound task to schedule. It has 2 inputs, a small input on server A and a large input on server C. The task could be doing a join between 2 datasets, for example. The 2 inputs are in different racks, and the racks are interconnected using an oversubscribed network. To simplify the example, we consider 4 servers as candidates to host the task. And we represent the expected wait time to acquire resources on those servers, as well as the impact of the essentially I/O path on the performance of the task. So we know it's an I/O bound task. The scheduler could go for locality and pick server C for the minimum task runtime. However, the server is very busy, and it's not clear that the performance benefit obtained from locality is actually worth 40 seconds of wait time. So then the scheduler could go for minimum wait time and go with server A. But then there's actually a very large performance penalty in this case because we're reading a large volume of data across the oversubscribed network. But if we reason about both these factors at the same time, and if we're able to proactively reason about future resource availability, we see that the best outcome is actually server D, which trades off on both in order to minimize the overall task completion time. But we can only get to this result if we reason about essentially all those conflicting factors at the same time. And Apollo achieves this with estimation-based scheduling. It optimized the job performance by computing in estimated task completion time on the servers, and then it tries to minimize it. The estimate contains three parts. The initialization time, which is essentially the expected time to copies the binary required by the task on the target server. The wait time, which is derived from the wait time matrix, is the time it would take to wait to obtain the CPU and memory resources for the task. And finally, the expected runtime, including any impact from locality or network topology. We also use additional techniques that we cover in the paper to optimize when we schedule for a whole batch of jobs at the same time, whole batch of tasks at the same time, for example, when scheduling is staged, but they're out of the scope of this talk. So estimation-based scheduling allows Apollo to minimize the task completion time by considering all relevant factors together. The clusters and workload are dynamic. So some events can happen that make previous scheduling decision suboptimal. So for example, schedulers can make conflicting decisions, or the expected wait time can increase after a task was dispatched. Apollo defers the resolution of those conflicts. Rather than immediately rolling back essentially the request, the process node will just accept the request in the order it receives them. The scheduler then constantly reevaluates previous decision and compares them with the decision it would make now with the most up-to-date information. And if it detects that it would be faster to relocate a task, then it can trigger a duplicate. The full detail of the mechanics are in the paper, but to summarize, Apollo is made robust to cluster dynamic by using correction mechanisms. Early on, we highlighted the challenge of maximizing utilization. It was essentially challenging because we need to do this without affecting the performance guarantees to our users and the SLA. And on the other hand, there's a constant fluctuation of the workload, which makes this even more difficult. So it requires a mechanism that is self-adapting. Apollo maximized the utilization of the cluster using opportunistic scheduling. It allows the schedulers to use the remaining temporarily available capacity by scheduling tasks above their resource allocation. Such tasks can only consume otherwise idle resources, and they have much lower runtime guarantees than the regular tasks. For example, they can be preempted or terminated if the process node hosting them is under resource pressure. However, since those tasks can be essentially preempted, it's important to prevent starvation. So the schedulers can upgrade opportunistic tasks to regular tasks when they have the resources to do so. A challenge posed by this technique is to prevent a few jobs from utilizing the entire opportunistic capacity of the cluster. So Apollo first limits the amount of opportunistic capacity that each job can consume, but even with this, the opportunistic capacity of the cluster is heavily oversubscribed. And in order to allow jobs which are just entering the system to quickly get a share of the opportunistic capacity, the process node will randomly pick a task from its opportunistic queue when there are resources available and the regular queue is empty. This is a contrast with the regular queue task, which is essentially FIFO. The random decisions are weighted in order to average to a fair sharing of resources. So this mechanism, opportunistic scheduling, allows Apollo to maximize the cluster utilization. We've covered an overview of how Apollo meets the scale, challenge with the distributed and coordinated architecture, how it handles cluster dynamic with conflict resolution, and how it maximizes cluster utilization with opportunistic scheduling. We now cover an overview of how the system addressed those challenges in practice in our production deployment at Microsoft. First, we're interested in evaluating how Apollo scales. Well, Apollo has been incrementally deployed in many production clusters over the course of last fall. Each cluster contained over 20,000 servers, and in one cluster, we observe Apollo running 170,000 tasks in parallel and tracking 14 million pending tasks. We now turn to the second challenge, which is optimizing job performance despite a complex heterogeneous workload. Evaluating this is actually challenging from an engineering standpoint, simply because we're interested in the real performance of the job in the wild under real production workload, rather than the performance under benchmark conditions. Apollo's architecture allows to run multiple schedulers side by side and compare essentially the performance of jobs between them. So here, we evaluate the performance of Apollo in production by measuring the job latency, so the end-to-end completion time, of an important job which process logs to derive advertisement insight. We observe the performance over hundreds of runs over a 2-week period. We compare the performance of Apollo with the baseline scheduler, which is essentially the previous production scheduler lacking the use of estimate and the use of estimate to optimize performance and the essentially a coordination mechanism. We further compare Apollo with an ideal trace-driven simulator with an infinite capacity. First, we observed that that the baseline scheduler was impacted by a 40% slowdown under the weekly load variation. However, Apollo maintains consistent performance despite variations in the load. We see that Apollo leads to a 1.5x speedup over baseline and actually performs quite close to the ideal workload, to the ideal scheduler. The third challenge is to maximize the resource utilization despite a dynamic workload. We show that Apollo used the resources efficiently. On the graph on the left, we represent the share of the resource utilization broken down by opportunistic task and regular task. We see that on weekends, when the demand reduces, the opportunistic tasks increase their share of the essentially resource consumption, while on weekdays, the utilization is dominated by the regular tasks. On the graph on the right, we show that under weekday load, Apollo can sustain a median CPU utilization of 90%. Further, there's no impact to regular tasks. The regular non-opportunistic tasks maintain a queue length of less than 1 second at the 95th percentile. So we've covered an overview of how Apollo addressed those challenges in practice. We now cover some related work and conclude. There's been a number of related work in this important area over the last few years. First, there's been development in centralized schedulers which try to theatrically orchestrate all scheduling decisions in order to optimize job performance. Some examples are Quincy or Hadoop daily scheduler. There's the hierarchical scheduler which essentially decouple the resource management from the task tracking. And some work in that area include Mesos, Yarn, and Corona. And finally, there's also other decentralized schedulers like Sparrow and Omega that adopt topology similar to Apollo's. To conclude, Apollo adopts a loosely coordinated distributed architecture deployed to clusters with over 20,000 servers in production, makes high-quality scheduling decisions by minimizing the task completion time and maintains consistent performance, and finally, maximize resource utilization using opportunistic scheduling, which leads to a 90% median CPU utilization under load. Thank you. I will take questions.
Chris Kozirek, Stanford University. Very interesting work. So several companies and researchers have identified interference as a big issue in scheduling. So if you put a bunch of jobs on the same server, the clash on caches, NICs, disks, flash, and so on. Have you evaluated how the quality of your schedule with respect to interference? And my worry is specifically that if it affects wait time, it's fine, and you will catch it. But it will also affect runtime. So your workload, because of an unfortunate placement, may be running 2, 3, 4 times slower than it should if you get a good placement. How do you adapt for that?
Okay, that's a great question. Thank you for asking. Like many of the related work, Apollo depends on robust isolation on the, essentially on robust local resource management on the, essentially the servers. So some work, some relevant work in this area include CPI2 from Eurosys, and essentially there's also like Linux containers and Windows job object that can be used to essentially isolate performance, but I'm not sure that the technology is yet to the level you're describing, and we can discuss more offline.
Have you measured the problem?
No, we did not measure the problem.
Thanks.
Henry from Stanford University. When you look at maximizing resource utilization, do you also consider the maximization of disk I/O and memory usage as well as CPU?
That's a great question, thanks. In our system, we observe the bottleneck as being the CPU, so that's the primary resource we're essentially trying to optimize for. And essentially we're not really, we're concerned about the utilization of the memory. We're not publishing any numbers on memory utilization in this paper. And with regard to disk I/O, yes, disk I/O utilization is also very important in order to maintain good performance. And again, Apollo is relying on essentially the I/O scheduler to do its job correctly. We can discuss more offline if you have a further question. But a good question. Thanks for asking.
Thank you.
Hello, Malte Schwarzkopf from the University of Cambridge. So I have a question regarding the sort of target workload for Apollo, because I think your formulation of how you use wait time and runtime and these sorts of things to work out the optimal schedule is sort of dependent on assuming a batch workload, right? You assume that tasks have a time at which they complete, they do some work, and then they run to completion. Some of the related work has also looked at placing service tasks, such
yes.
as long-running web servers and these sorts of things. Am I correct in assuming that, as you've described it right now, Apollo is not particularly suitable to dealing with this? And if so, do you have any thoughts on how you could extend it?
So we can model long-running services as essentially infinitely running processes, which essentially blocks out rows and columns of in the wait time matrix. So essentially to say that those resources will never be available, and this.
Sure, but then you don't get a good schedule for them, right? If there's no trade-offs that you can make if you say that they will run forever. And of course, there are better and worse placements for these things as well, right?
That's correct. So essentially, Apollo is really a scheduler for essentially cloud-scale big data processing. That's really our target workload. And however, the architecture also supports sharing with other schedulers, and we can see sharing multiple schedulers, one service scheduler also in that same architecture, and then that would solve the problem.
All right, thank you.
Thanks. Done?
Yep. Do you want to? I have a couple more minutes. So you can keep up.
Sorry, I thought you were.
Alternatively, you can rewind.
Hi, I'm VJ from Twitter. I think this is kind of interesting, and I echo some of the questions others had. But my main question actually is, how do you think you could extend your system to deal with eliminating the discrepancy in load across clusters? Because this is something when I worked at Google we spent a lot of time trying to solve. Because you have clusters of 20,000 computers, you have batch jobs and jobs that could work whenever there's free resources, and sometimes some clusters are really loaded and sometimes others aren't, and that was always a problem.
I'm sorry, I'm not sure I understand the question. So you're talking about how does it balance the load? Is that?
No. So you were talking about how you can run jobs on one cluster, right? So the scheduler operates within a cluster. Is that correct?
That's correct.
Okay. So, but in Microsoft, you probably have 20 clusters, right? And the instantaneous load utilization of CPU and memory varies across these clusters. So in cluster A, CPU may be fully utilized, and cluster B may be pretty idle. So when I schedule a new job, ideally in the real world, I'd like that job to be scheduled in not only on the appropriate machines within a cluster, but also on the appropriate cluster. And I was wondering if you guys thought about that.
So yeah, that's a very interesting question. Essentially, Apollo's workload, if you consider like the heuristic used, so some of the heuristic like essentially include data locality. So the assumption is that you would run the job in the same cluster where most of your data is. So that would be the prime concern when deciding which cluster to schedule your job to. And that's what our users do in practice. But no, Apollo doesn't really look at deciding which cluster to schedule tasks in at this moment. This is not work that's included. But it's actually very interesting work. Thanks for asking that question.